just like, mathematical proof is one kind of proof among many, okay, there's many kinds of mathematical proof as well, okay? And I'm going to show you, like I said, there's lots of them, but I'm going to show you 4 of them, and I'm going to illustrate them with these boxes in front of me, okay? So, maybe you've been like, this is not mathematical stuff, don't need to worry about this, okay? Now you want to pick up your pen if you haven't already. Let's walk through 4 kinds of proof, and I'm going to illustrate them for you, okay? With these boxes, 1, 2, 3, 4. 4 kinds of proof. And you're pretty familiar with most of these, okay? The kind of proof you're used to at the moment is direct proof, okay? Even though we might not have called it that. If you want to prove something, you take a bunch of properties and theorems and qualities you know about something, right? In the case of maths, we're thinking about numbers and geometry and space, right? And you use those properties to come up with a conclusion, right? So suppose, here we go, 4 boxes. I want to prove that these 4 boxes can be pushed over, okay? That's all I want to prove. That's all I'm interested in. Okay? Can I prove that these 4 boxes can be pushed over? Now, how would direct proof approach this? Well, it would look at the boxes and say, look, what do we know about these boxes? Okay, what can be known about these? What kinds of properties do they have? Right? And then using some of those properties, we don't need to use all of them, we just need some of them, enough to prove what I just said, that the boxes can be pushed over. Okay? So, for instance, I might go and weigh all of the boxes and say, well, I don't know how much one of these weighs, like 10 grams or something, not very heavy. Okay, and then I can say, well, I know I'm not the most muscular person in the room, but I can push over masses that are under 10 grams. So I can push all of these over. I'm using a property that all of them share, right? And I can prove, therefore, they're all under 10 grams. I can push things over that are under 10 grams because I can lift. And so therefore, done, proved. Okay, and that's the way direct proof works, right? You get like a triangle, and you find out what properties you have about it, and you prove some, Pythagoras' theorem, whatever. Okay, that's direct proof. Another kind of proof that we're interested in, which you don't use much because it's tiring, not just because of the name, but it's proof by exhaustion. Now, again, you often don't call it that. Often it's called proof by cases, okay? Because the idea is, you take all of the things you're looking at, every possible instance, and individually you prove them. You take every single one, every alternative, every way this could possibly exist, and then you just do them one by one. So we call it proof by cases because you often have to divide up, there's 50 situations. You divide them up into 3 different types and you can prove them each one by one. Okay? So how would I do it here? What would proof by exhaustion look like in this case? I've got 4 boxes, right? I go to the first one and I say, can I push it over? Yes, I can. Okay, great. Case 1, tick. Right? And then I go to the next one and I see if I can push it over. Case 2, tick, and so on. Right? Proof by exhaustion. In computing terms, we often call this a brute force proof. Okay? It's simply just going through all of them, which is often how people break passwords. People use common words. If your dictionary is big enough, you just try all of the words and eventually you'll get one. Okay? All right, number 3. Not a very common one, okay, but proof by contradiction. Proof by contradiction, okay? Now, how does proof by contradiction work? What did I want to prove? What did I set out to prove before? That all of the boxes can be pushed over, okay? So proof by contradiction assumes, or considers rather, what would happen if that weren't true? What would happen if these boxes actually all couldn't be pushed over, okay? Then you take that idea, and just like with the first one, you consider it, you work with it, and then eventually you come down to a conclusion where there's some kind of inconsistency, some kind of thing that's impossible. Like there's some box and it can be pushed over and not pushed over at the same time. You're like, that doesn't make sense. It's a contradiction in my argument. So therefore, what I thought about before, that they can't be pushed over, it must be wrong. Because if I take that to its logical conclusion, it breaks down. Okay? So that's proof by contradiction. There's a famous one for the irrationality of the square root of 2, or square root of 3, or whatever. That's the most famous one that you guys have to deal with sometime in year 9. Now, that leads me to my last one, which is our new topic for this term, which is proof by induction. Okay? So if you want, you can put a heading now, which is mathematical induction. It's important, by the way, that you make the heading mathematical induction because it's often called proof by mathematical induction. And this induction is actually quite different to induction in general terms. There's inductive logic and there's deductive logic in sort of philosophy and argument and epistemology. But this is a special kind of induction, okay? So I'll let you work out the words later. How does it work? Proof by induction. Look at my 4 boxes, okay? Now, I'm going to make some parallels to these 2 kinds of proof here, all right? Firstly, I'm going to make a parallel to the proof by contradiction. Remember I said the basic idea was you have to make an assumption, right? In the case of proof by contradiction, you assume they can't all be pushed over, okay? And then you see what happens if that's the case. Proof by induction also makes an assumption, but I'll talk about what the exact assumption is in a second, okay? Secondly, direct proof, okay? Now, what did we do with direct proof? We looked at the different boxes and the properties that each one had, okay? Now, proof by mathematical induction does something similar, but it includes something different, which direct proof doesn't have, okay? Which is, look carefully at this, right? Proof by induction very carefully considers what the gaps are between these boxes. Direct proof doesn't care what the gaps are, doesn't care what the relationship between these boxes is, right? It just thinks about what does each box have in common? What does each box have as its properties or qualities, okay? But mathematical induction, right? Critical to the way it works is the fact that these boxes have a relationship to each other. I didn't just put them randomly, okay? There's distances between them that are going to be important for us in a second, okay? So I'll rehearse all of this in a second and write it all down, but let me show you how mathematical induction would work. I would have a look at these boxes and I would say, well, look at all these gaps, okay? Now I noticed that the gaps for each one are pretty short, okay? For instance, you know, one of the boxes is not out here, right? It's not so far away that they can't touch each other, okay? So in other words, they're close enough that if I push one of them over, just pick one, any one, okay? And in fact, it's very important that it can be any one of them, okay? If I pick this one, or any arbitrary one, I can show that because this distance is small enough, it'll push over the next one. I push it, it collides, and it'll make the next one fall over, okay? Now, if I can prove that, if I can show that all the gaps are small enough that if I push over any individual one, it'll push over all the subsequent ones, that's pretty good news, right? That means something very significant about all of them, right? Now, I still haven't proved that they can all fall over. I need one more piece of information. Let's start from this side, because that's your left-hand side. If I can prove that pushing over one of them will push over all the subsequent ones, right? And then I prove that I can take the very first one and I can push it over. I can take the first one and it can be pushed over. I do have the muscles to do the 10 grams, okay? If I put those 2 pieces of information together, then I should be able to prove that they all fall over, right? Now, I'm going to put them closer together just to make sure I don't embarrass myself by, you know, the demonstration not working, okay? Fingers crossed. I say the gaps are small enough. Can I push the first one? Yes. They fall. Cool. Hooray. Right, now, okay. All of that, just for that. Okay, now, how does it work? How does it work actually mathematically? And let's stop talking about boxes, shall we? Now they don't want to stand up. Okay,